Hello, everyone. So let's move on to learn more about linked list. We have learned about stacks, we have learned about queues in this module until now. Now let's next, we also have learned about, along with learning about queues, we also have learned about priority queues in our last video. And now we will next learn about linked list. Linked list, as the name says, is nothing but a linked list, right? So every piece of linked list, every node of linked list has two things into that. First is a data value, what it's storing. Second is a pointer to the next. This pointer connects that item to the next. So usually we represent linked list as something like this. And each node has a value that can be stored inside this. We can store A, B, C, something like that. And then each node has a pointer to the next item of that list. This is your linked list. To insert a new node in the linked list, you need to do some more operation rather than just using push and pop as to insert and delete as you used to do, or as we discussed while using stack queues and priority queues. While in linked list, it would depend on where you want to insert things to. So remember three basic steps when you perform operations of insert and remove on linked list. First, you need to disconnect. Second, you need to insert or remove. Third, you need to reconnect things back again, because otherwise you will have two linked lists as a result of disconnecting and removing something if you forget to reconnect the linked list back again. So let's say if we have a linked list, something like this, A, B, C, D, 4 items, and we want to remove B out of it, what we would need to do in order to remove B is we cannot just delete pop B. That's not an operation we can do in linked list, but rather what we would do to make this happen is we would say that A's next is now B's next, right? We will, rather than A's next pointing to B, we would say that disconnect it from B. Let's use some other color. Let's use orange. So rather than A pointing to B, we would say disconnect it from B and point it to C. So A's next will become B's next. And then we would say that delete B. And that's when your item is deleted. So we did disconnect. First, we disconnected A and B. Then we did our reconnect, and then we also removed the item. If you are adding an item to a list, let's say if you want to add an item over here, item Z, then again we need to follow these three steps without forgetting. First, we need to disconnect something. Here, what we would disconnect is a link between C and D. Then we need to insert. So we would say that now C is next is our new item, that's Z. And we will say Z's next is whatever the C's next used to be. So that's D. That's our reconnection or insert step. And then finally, yes, we have a new linked list that has A, B, C. If we didn't remove the B, if we remove the B, we won't have B. So we'll have A, C, Z, and D. So imagine it as if you have items, and if you are removing things, then what operations you need to do. If you forget to do any one of the order of these operations, how you do might vary back and forth, but you need to do all three items in order to get through your insert or remove. You can insert item either at the front of the linked list. When you have a linked list of different items, then you can just insert things at the front. Inserting things at the front is easy because in that case, you don't have any other item in the front of the front, right? So you can insert things at the front. You can delete things from the back. You can delete things from the front, or you can insert things at the back. So all the operations insert and delete can be done at the front, can be done at the back, or can be done somewhere in the between. Doing these operations in between is something that's most complicated. Doing it in the front or back, depending upon what operation are you doing and what pointers do you have. If you have only a front pointer, and if you want to add an item to the back, then you have to traverse your front pointer until front dot next, front dot next, front dot next, until you reach the end of the list. And then you would say that, okay, once you reach the end of the list, then that end items next then becomes your new item. So depending upon what pointers you have, you need to logically think of the operations. If you have a back pointer, then inserting and removing things from the back also becomes easier. But by default, a linked list has just the front pointer. To remove a node, to insert a node, your logical steps that you need to follow are same. Try to draw it down and then figure it out. So let's see an example. Your linked list, in order to include from your STL library, you would need the header file d_node.h, which stores the data object. So this node, each node that you initialize using this header file, that would have the data object and it would have the pointer to the next node, same as what we need. So it will have some place to store the data and the pointer to the next node. How it looks like is it's implemented using templates so that you can use it with different data types. The class node has different public members and member functions, data members and member functions, where you have pointer next. You also have constructor of the node, parameterized constructor, and the default constructor. What these constructors says is if you have an item, then it would store the item in that node, and the next by default will always point to now. If you don't have an item, then it wouldn't store anything into that. So it will initialize an empty node, but the next of the empty node will also point to null. So by default, when you initialize the node, the next always points to null. Then depending upon how you write your code, you say what items are connected next. Let's see an example of that. So let's say that we included our header files, everything that we needed. We included that d_node.h. Then we started writing the key part of using and making our linked list. So let's say we want to initiate 4 nodes. So we used of type int. So we used node type int. It gives us P, Q, R, and S, 4 nodes. Then we are saying that we declared 4 nodes in our first command. Then we are initializing each of them. We are saying that the P is storing, let's write in this way so that we differentiate the item that's being stored from the item, from the name. So we declared 4 nodes, node pointers, P, Q, R, and S. This is how you would declare by using pointers when you want to use the linked list from the standard template library. You would say that P is storing 10. So this would give you 10. By default, it points to null. Q is storing Q is storing 8, and the next pointer of the Q is pointing to P. So this command, the second command, will give you something like this. Then you are saying R is a new node that is storing 7. By default, your next is pointing to null. Then you are saying that R's next is Q. So this command will do is your R's next, it will link this to Q. Q is right here. Q is storing 8. When R's next is linked to Q, automatically anything that's with Q just remains by itself as it is, because we have not changed anything with that. And then what you are doing is you are declaring S as a new node that's storing 9. Again, the next is null. The S next you are saying is P. So now this is your P, this is your Q, P, this is your R, Q, this is P. You are saying S next is P. So what it will do is we'll have your S, and S next will become P. P is storing 10. But then you have also these other elements that are pointing, right? There is another chain that's pointing to R, Q, S, P. So what we are doing next is we are saying that Q's next is equal to S. So initially Q's next was pointing to P. We are removing that from here, and we are saying Q's next is now pointing to S. And then we are saying C out our node value, and then we are moving our pointer to R equals to R node next. So we are starting from R. When we do the C out, it will print out 7 from here. Then when we do this command, R is equal to R next, our pointer will go next to Q according to this linked list. Like this is our last state of the linked list, right? Before we start printing this. So then it will print out the value that's there in Q. Then from Q, it will go to that's next, right? We are just saying it as R. So from there, it will go to its next node. So that's S. Whatever value is in S, it will print out that. And from there, again, it will go to its next, the pointer. And when it goes to it next, it ends up in P, and it will print out the value in P. So this is how you would frame a linked list. This is how you would modify the element. What we did here is we modified the element, we inserted. So until here, we were making this linked list. And then what we did is we inserted 9. We had 7, 8, and 10. And we inserted 9 between 7, 8, and 10. So we inserted 9, we made this next point to this, and then we made this 8 point to this 9. So this is inserting the code for inserting an item in between the list. And then finally, we printed the whole list by using the next command. It's important to understand that when you use next command, you are just shifting the nodes, and that's why the name doesn't matter. Whatever node you will be in your last state. When you use the next command, you move to in your linked list, you progress to the next node and then the next node until so on and so forth. Let's briefly see one more problem. If you are using, so we have different types of linked list where we say it's singly linked linked list if it's all the items just connected with a single next pointer. Sometimes the other type of linked list includes doubly linked list that has both back and forth pointer from each. So it has back and front of each node. It will have back and front, back and front. In the same way, every node has, rather than just having the next pointer, it also has the front pointer for doubly linked list. Front, it always points to the first node in the linked list. As I just said, by default, your STL class, the linked list of STL class gives you just the front pointer. You don't have the back pointer, but you can implement your own, you can modify this class in the way you want. You can add new function and then you can add a back pointer if you want. So let's see an example when the list is empty and front equals to null. When the list is empty, front is equal to null. That's how you identify that the list is empty. There is nothing in your linked list. The example over here, what we are doing in this example is we want to print the linked list. Can you try to fill this blank over here? This is very simple, right? The blank is just called next. If you understood our last example, this should be very clear to you. Then we can do some another operations like adding and removing the nodes. If, as we saw in that detailed example in our code, I think you should be able to fill these blanks by yourself. Please try filling them. If we want to add a node, then what we would, so if we want to, if the state of a linked list is something like this and we want to add this node between these two, then what are the steps we would do? And if you want to, if our state of the linked list is something like this, and if you want to remove this node, then what are the steps that we need to do? This can be done in a couple of different ways, but one of the correct way to do it is that new nodes. So this is your new node. You would say that depending on where you assume your current pointer to be, you can use a priv and current, two type of pointers. So if you are using your current pointer to be at the location where you want to insert, then you can say that the new nodes next, if this is your cur, then you say that the new nodes next is equal to cur, and previous node, if this is your prev, then you say previous nodes next is now equals to new node. In the same way, when you want to delete, it depends on where you assume your cur and next prev pointer to be. When you want to delete, then you want to say that if your prev pointer is here, and if your cur pointer is here, then what you want to say is your prev's next is now your cur's next. In that way, you are linking from here to here directly. And then finally, you would say delete cur. So inserting the item in the front, that's the easy part. You can add new items in the front in your linked list. You can delete the items from the front in your linked list. In order to delete the items from the front, can you quickly try to fill these two blanks over here? How would we delete the items from the front? Hopefully you have the correct answers here. In order to delete the item from the front, here we will have front next, and then we would delete, right? So we would advance our list and keep deleting the front. That's very easy. And if we want to delete the entire list, again, we will have front next. So until the whole list is empty, that we will know when our front is not equal to, until our front is not equal to null, we'll keep iterating. So as soon as our front is equal to null, we will know that our list is empty, and that's where we'll end. Finally, removing the target node. Again, it's simple as we saw before, but depending on your prev and current pointer, you would want to take steps to initialize and then find out the target node that you want to delete by processing your pointers by next, 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 next. And then finally recall how we removed and reconnected our list. So there are three important steps: disconnect, insert and remove, and then again reconnect back. As we discussed that the stack and the queue, they are adapter containers. So they are constructed as a wrapper using something as the core container. The linked list can serve as a core container to implement stack and queue. The adapter containers like stack and queues. So next, let's see that how can we implement both these stack and queue by using a linked list. Let's start with the stack. So in the stack, what's the purpose that we want to do? We want to pop things by removing, let's say that the pop is equivalent to remove from front, and we want to push if we are, as we know that in stack, both pop, push and pop operations are done at the same end, right? That we call as top. Now, if we are doing remove from front, that means if you want to implement stack, then we need to do also insert at front. So in order to implement the stack by using linked list, what we can do is we can have a structure like new node, and which identifies, which initialize a new node. You have an item that you want to store in the node, and you say that this is the front of the node. If the front is not equal to null, that means your list is not empty. Then you do different operations where you say that then new nodes next is equal to front. This front is the item that you want to insert in your linked list. So then you say the new node is the item that you want to insert. So you say the initially you had a linked list. If that linked list was empty, then you say new nodes next. If it's not empty, that means you had a linked list already. You checked if it's not empty. In that case, the new nodes next will become the front of whatever the linked list that you already had. And now your front needs to move to the new node, right? Because that's your new front. So that's this command. Else, if the linked list is empty, if there is nothing, then that's pretty straightforward. Your front is equal to new node because there's only one node, and that node is your new node. So that becomes the front. So this is the simple steps to using linked list. How can you implement stack? And the step to implement stack that we are doing here is we are implementing push, the step, insert at the front. There is one more step to implement pop. That is, we want to delete from the front, right? How would you implement pop? In order to implement pop, we are initializing two pointers, front and pointer P. Then we say that if front is not equal to null and back is not equal to front, assuming that we have a linked list that has two pointers, one at the front and one at the back. This is your front pointer, and you have another pointer at your back. These are assumptions. When you start writing your code, you can make your own assumptions in your piece of code, right? Because it's your world. You can assume whatever you want. And then depending on your assumptions, you define things and you declare things and then define them. Initialize them, declare them, and define them. So here we have two, in this piece of code, we have two pointers. And we are saying if both this is not equal to, if front is not equal to null, and if front is not equal to back, that means we are checking two conditions. First, we are checking if list is not empty. And second, what we are checking is if list has more than one item. Because remember this, what we are implementing now is a pop. In order to implement a pop, if it has more than one item, then the state at which your linked list will end up is having one less item than whatever we had before. But if it has just one item, then your linked list ends up in like having no items as your end state. And if it does not have any item, then you cannot do pop. So the resultant in this three case where you do not have any item, you cannot do pop. If you have one item, the resultant is an empty list. And if you have more than one item, then you have a list that just one item less than the previous linked list. These are three different cases, and that's where we have this if condition. We ensure that we are in that third case where we have more than one items for sure. In that case, when we have more than one item, what we do is we say that, hey, I have a new pointer P that we declared here, initialized here. So I have a new pointer P, and P is equal to front. We say that my pointer P is pointing whatever the front pointer is pointing. And then we say that, okay, now I want to advance my front pointer to its next. So we say front is equal to front dot next. We move the front pointer to its next. And then we say, okay, after we are done with that, delete whatever the P is pointing to. We deleted that item. In this way, we popped the item outside our stack from the front. We removed the item from the front. There are other cases where else if front is not equal to null and back is equal to front. So this is exactly what we were talking about, the case of having one item in the list. If you just have one item in the list, right, that item is your front. And when you want to delete that, what you do is, okay, my P is equal to front, and then delete P. Or you can just do delete front, right? Rather than these two commands, you can also use delete front. So there are multiple ways in which you can frame your own code to perform the same task. This is what we are discussing here are just an example, one way of doing things for you to click your own ideas to start doing your own things. And then if we can have further else list if you want to do more complicated things in the stack. that you are implementing if you want to give other functionalities to that stack. In the same way, we can implement a queue as well using linked list. Even queue is an adapter container. So underneath queue, it's using something else, and it could as well be using linked list underneath it. So what's the difference now with the queue is that just front pointer is not sufficient. You would need a back pointer as well. The operations of the queue that we do is we pop from the, where do we pop things out of the queue? Front, but we push things at the back. So back pointer to the last node in the list, this pointer is going to help you while you are doing push. We also use the back pointer here in this piece of code in order to check how many elements are there in the list. In case if you don't have a back pointer, the comfort of having a back pointer over here, you can still write this piece of code without the back pointer, where you can you can advance your front pointer to its next until front's next is equal to null. That's how you compute the size of the linked list. Once you know the size of the linked list, then you just do an if else check. If the size is 0, then this. If the size is 1, then this. If the size is greater than equal to 1, or else something else. So you don't mandatory need the back pointer, but if you assume that you have the back pointer, then it makes your world easier. For the queue, same as in order to implement queue, it's good to have a back pointer because it allows us to access the back of the queue. And in this case, we do need to access that because queue has insert in one direction and exit from the other direction, opposed to the stack where insert and exit are both from same direction. We assume that direction is front. Again, that was another considerable assumption. You can assume that the insert and the push and pop that's happening in stack, we assume that that's happening from the front rather than front. If we would have assumed that's happening from the back of the linked list, then that would have made our world a nightmare, right? In that case, if you don't have a back pointer and you want to do all the operations at the back, then you need to do much more complex operations compared to this piece of code over here. Again, your assumptions, rules, how much work you want to put in. So make smart assumptions when you are writing any code. Okay, so how we will implement a queue over here? We will say a new item. We will declare a new node that has an item. If we want to add the item to the back, right? That's the operation we are implementing. That's our push. What we would say is if front is not equal to null, that means your list is not empty. What we would do, fill in the blank by yourself. After these all examples, you should be able to do these things at like the snap of fingers. If front is not equal to null, that means list is not empty. How would you add a thing at the back? Remember that you have assumption of back pointer. You have a pointer in your linked list, which is not empty. You confirmed by the if condition. You have a back pointer that's pointing to the last element. And you have a front pointer that's pointing to the front element. How do you add item at the back? Back next is equal to new node. AirPods went out of charge. What about the second line? Back next. is equal to new node. What about the second blank? Else, that means if the list is empty, how would your insert push to a will affect this? If the list is empty, then that's the only element you would ever have, right? So then your front is equal to new node. And your back is also equal to new node. So if the list is empty, the new node, whichever you are inserting or doing push, is the only node that you have. So your front and back both are pointing to the same item. How about implementing the pop? Implementation of the pop for the queue. Do you have to do anything different from how you implemented pop for the stack? No, because even for the stack, you implemented pop as deleting item from the front. And when you are implementing a pop for the queue, again, you have the linked list, you are deleting item from the front. Your pop will be same as whatever you would do for popping an item outside the stack, even for the queue. So pop is same as stack. Same as pop from stack. Again, stack implemented with linked list. Okay, so then this concludes our lecture of linked list. Um, I hope you learned something new in this lecture, and these discussions would trigger more ideas into your mind of doing more complex operations using linked list, using queues, using stacks, and actually trying to apply, like look around you and see where you can apply or use these data structures that you have, and try to practice coding, because the more you practice, the more well versed you will get with that. In order to practice, first you need to think what you want to do, right? You need to think your problem. Then you need to connect your problem with data structures. So what data structures can you use? Then you need to code your algorithm for that. So using this data structure, how can you solve the problem? That's your algorithm. Once you are done with your framing your logical algorithm by yourself, then you might want to write a pseudocode. Pseudocode is the piece of code like what we are discussing um, in this in this slide deck over here. And by the how pseudocode differs from the main code is that it does not have some implicit lines of code like hash include iostream.h. This that you can miss while you are writing pseudocode. You can have some simplistic syntax of your own. So pseudocode is bit more bit more syntax oriented than algorithm. Algorithm is just your logic, just like how many loops you will have, from where you will start your loop, where you will end your loop, how many arguments you would need in the function, how many functions you would have, what you will do inside each loop, what you will return, what will be your input, what will be your output, something like this. That's your algorithm. Once you are done with your logic, then you connect that with C++. That's your pseudocode. Finally, when you're done with the pseudocode, you can write your final actual code, type your code, and then try to execute that. Once you are done with the code, your job is not yet done. Until you get the correct output, you need to debug your output. So you need to, if something is going wrong, you need to see what's going wrong and why it's going wrong. After you are done debugging, still your job is not done. Then your job is to make things more efficient. And that's where we will be discussing. Uh-oh. Okay. Yeah. And when we talk about efficiency, that's where we'll be discussing the next topic of this module. That's the complexity analysis. So any algorithm you code, there is an efficiency connected with that. How do we compute this efficiency? And how do we ensure that things we code are more useful and more efficient, more optimized, rather than just solving the problem? We want to solve the problem in a better way. So these are the steps. Try to think of different applications, try to go through these steps until wherever you can. And that's what will make you a better and better at this drill of understanding a problem, writing a code to solve that problem. And that's all we need to excel or to get an A grade in this class. Okay, so then next we'll continue discussing about the complexity analysis of algorithm. If you have any questions on stacks, queues, linked list, everything that we discussed until now, please see me in my next office hours. Thank you.